Black diamonds changed the way dark gemstones were perceived. For a time, they represented modern luxury, bold, unmistakable, instantly recognizable. But luxury evolves. Today, a different category of dark gemstones is gaining quiet momentum among collectors who value discretion over display. These stones rarely rely on sparkle. They rarely appear in mainstream marketing, and in many cases, their rarity becomes visible only after closer observation. Formed through uncommon geological conditions, rare chemical environments, or structures that challenge traditional definitions of what a gemstone should be. Each material in this list represents a different expression of quiet luxury. Not louder, not brighter, but often more difficult to replace. From ancient minerals formed billions of years ago, to gemstones whose internal structures remain subjects of ongoing scientific study, these are 10 dark gemstones redefining prestige beyond black diamonds. Number 10 begins with a stone long mistaken for something else entirely, yet now increasingly chosen for exactly that reason. Ranked 10th, black spinel, the stone that quietly replaced what everyone thought was rare. At first glance, nothing about this stone appears unusual. No dramatic flashes of rainbow light, no intense sparkle engineered to capture attention across a crowded room. No visual urgency demanding immediate recognition. Just a deep, controlled black surface that seems almost intentionally restrained. And yet, this is precisely why black spinel has quietly entered collections that once defaulted to black diamonds. For decades, black diamonds became associated with modern luxury because they looked bold and unmistakable. Their presence was obvious. Their identity required no explanation. Black spinel follows a different logic. Its appeal does not rely on instant recognition. Historically, spinel has existed in the shadow of more famous gemstones. Some of the most celebrated rubies in royal collections were later identified as spinel only after advances in mineral analysis clarified their true composition. This pattern repeats itself today, but in reverse. Collectors increasingly choose black spinel not because it competes visually with black diamond, but because it does not need to. Its color is not created through heavy inclusions that disrupt internal structure. Instead, the darkness appears controlled, even calm, revealing a material that maintains clarity beneath its surface rather than masking it. Under magnification, the difference becomes more apparent. Where many opaque black stones absorb light aggressively, black spinel often displays a more balanced interaction with light, producing subtle reflections that feel deliberate rather than decorative. This creates a visual effect sometimes described by collectors as confident neutrality. Nothing about the stone attempts to persuade. Nothing about it feels excessive. Its presence is defined more by stability than spectacle. And this is where quiet luxury begins to diverge from conventional gemstone marketing. Rather than selecting stones designed to signal value immediately, some collectors choose materials that require context to appreciate fully. Black spinel exists comfortably in that category. It does not introduce itself loudly. It does not rely on trend cycles. It does not depend on widespread recognition to maintain relevance. Instead, it reflects a different kind of luxury logic, one where the material itself remains unchanged while perception evolves around it. In many ways, black spinel represents an early transition away from gemstones chosen primarily for visual intensity toward those selected for their composure. And once composure becomes the defining trait, the entire hierarchy of dark gemstones begins to shift. Because some stones do not appear extraordinary until the criteria used to evaluate them change. Number 9 reveals a material that challenges the very definition of what a gemstone is supposed to be. Ranked 9th, Apache tears, obsidian, a gemstone without a crystal, yet impossible to replicate naturally. Long before laboratories learned to grow perfect crystals, nature occasionally chose a different path entirely. Instead of allowing atoms to arrange themselves into ordered geometric structures, certain volcanic environments cooled so rapidly that crystallization never had time to occur. The result was a material that behaves like a gemstone, yet technically never became a crystal. Apache tears obsidian emerges from that interruption, formed when silica-rich lava solidifies almost instantly upon contact with cooler air or water. Obsidian develops as natural glass rather than a mineral, with a repeating lattice. In most contexts, this rapid cooling produces opaque black masses with a surface appearance closer to polished stone than transparent gem material. Apache tears represent a far more selective outcome. Within certain nodules, internal clarity remains partially preserved, allowing thin edges to transmit light with a subdued smoky translucency. This optical restraint creates an effect that feels intentionally controlled. Never bright, never decorative, never obvious. Unlike faceted stones designed to maximize brilliance, Apache tears communicate value through absence of visual noise. Their surfaces appear quiet, uninterrupted, almost reserved. In luxury design contexts, increasingly influenced by minimalist architecture and matte materials, this type of visual behavior has become more relevant than intense sparkle. The material does not compete for attention. It stabilizes the composition around it. From a gemological perspective, volcanic glass presents a paradox. Because it lacks a crystalline structure, its internal arrangement remains amorphous. Atoms positioned without repeating symmetry. This makes each specimen dependent on extremely specific cooling conditions to achieve internal consistency without excessive fracturing or clouding. Achieving uniform translucency within such a chaotic formation process is uncommon. Achieving it naturally is even less predictable. This unpredictability creates a form of scarcity not based on limited geographic location alone, but on the statistical improbability of favorable cooling conditions occurring repeatedly. Collectors drawn toward understated materials often recognize this distinction. A stone does not need to demonstrate optical fireworks to convey rarity. Sometimes restraint itself becomes the defining feature. Apache tears rarely appear in high-profile jewelry marketing campaigns. They are seldom positioned as centerpieces in luxury retail displays. And yet their aesthetic language aligns closely with broader cultural shifts, favoring materials that suggest permanence without theatricality. In environments where polished surfaces and reflective brilliance dominate visual expectations, the presence of a naturally formed glass gemstone with muted translucency can feel unexpectedly deliberate. The material seems to exist outside conventional gemstone hierarchies, not louder, not brighter, simply quieter. As quiet luxury continues moving away from easily recognizable symbols, materials that require closer observation begin to carry increasing relevance. Because once attention shifts from immediate brilliance towards structural nuance, even the definition of value begins to evolve. Number 8 introduces a gemstone whose complexity is almost entirely invisible without magnification, yet whose formation conditions are among the most chemically specific in gemology. Ranked 8th, Melanite garnet, darkness engineered by chemistry, not absence of light. Precision in nature is rarely accidental. Within the garnet family, a group known for its wide color diversity, one particular variety develops a depth of tone so controlled that its surface appears almost deliberately engineered to suppress visual distraction. Melanite garnet forms when titanium replaces part of the silicon normally present in the andradite garnet structure. This subtle chemical substitution alters the way light interacts with the crystal lattice, increasing absorption across visible wavelengths until the gemstone presents a near-uniform dark appearance. What appears visually simple is, in reality, chemically specific. Trace element balance must remain within a narrow range to achieve this level of saturation without destabilizing crystal growth. Too little titanium, and the stone retains brown or green undertones. Too much, and structural integrity may be compromised during formation. Nature rarely repeats such conditions consistently. As a result, fine melanite specimens tend to circulate quietly among collectors already familiar with garnet complexity rather than entering broader commercial awareness. Unlike high-dispersion stones designed to display intense brilliance, melanite communicates through surface confidence. Its luster is polished but restrained, reflective but not attention-seeking. The effect is often described as architectural rather than decorative. Under magnification, the crystal reveals a dense structural uniformity that contributes to its visual composure. Internal transparency exists but remains subdued, producing reflections that feel contained rather than amplified. In design settings influenced by matte metals, monochromatic palettes, and minimalist geometry, stones with this type of visual discipline create continuity rather than contrast. They integrate rather than dominate. From a geological perspective, titanium incorporation into garnet requires a specific chemical environment during crystallization, typically associated with metamorphic conditions where pressure, temperature, and element availability converge within narrow margins. Each variable must align. Each imbalance reduces the likelihood of producing materials suitable for gem use. Scarcity in this context is not created through dramatic visual features, but through improbability of formation chemistry repeating with precision. Collectors attentive to these subtleties often view melanite as an example of rarity that does not advertise itself openly. Its presence signals familiarity with gemological nuance rather than preference for visual intensity. In markets where many dark stones compete through opacity alone, melanite distinguishes itself through compositional intent, a gemstone whose darkness is not incidental but structurally encoded. Understanding this distinction begins to change how dark gemstones are evaluated. Because when color becomes a function of atomic substitution rather than superficial appearance, the concept of luxury moves closer to material literacy. Number 7 introduces a stone whose optical behavior remains unexpectedly complex despite presenting an equally restrained exterior, demonstrating that darkness does not eliminate interaction with light but can refine it. Rank 7. Black zircon. Optical complexity hidden beneath a restrained surface. Density influences perception long before it influences appearance. Among naturally occurring gemstones, relatively few materials possess an optical structure capable of bending light with measurable intensity while simultaneously presenting a visually dark body tone. Black zircon belongs to that rare category. Chemically composed of zirconium silicate, zircon develops under geological conditions often associated with granitic environments where trace radioactive elements may be present in small quantities. Over immense periods of time, internal radiation exposure can subtly disrupt portions of the crystal lattice, altering optical behavior without eliminating structural identity. The result is a gemstone capable of exhibiting high refractive index and noticeable birefringence, properties more commonly associated with transparent stones, yet expressed here through a subdued, darkened presentation. This contrast creates a form of technical intrigue rarely visible at first glance. When light enters zircon, it slows significantly compared to its speed in air. The crystal structure divides the light path into 2 separate rays, traveling at different velocities, a phenomenon known as double refraction. In lighter-colored zircon varieties, this effect can produce visible doubling of facet edges. In darker zircon, the same phenomenon persists, but becomes more subtle. The optical performance remains present even when visual brilliance appears restrained. Such internal behavior introduces a quiet form of sophistication, complexity that exists regardless of whether it is immediately visible. For collectors attentive to gemological physics, zircon represents a material where value emerges through measurable interaction with light rather than decorative intensity. Even in darker tones, the gemstone retains a structural capacity for optical activity that many opaque stones cannot achieve. This characteristic differentiates black zircon from materials whose darkness results purely from surface absorption. Instead, the crystal continues to engage with light internally, producing controlled reflections that feel disciplined rather than expressive. Because zircon forms in environments that often preserve ancient geological records, individual crystals can also carry implications about the thermal history of the Earth's crust. Some zircon specimens have been dated to billions of years, making the mineral group itself one of the oldest known carriers of geological information. Although black zircon used in jewelry is not necessarily among the oldest crystals studied scientifically, its mineral identity remains associated with deep geological time and structural resilience. Within the framework of quiet luxury, such associations contribute to a perception of intellectual permanence. The stone does not depend on the surface drama. It reflects a material capable of maintaining internal order across immense spans of time. As preferences increasingly move toward objects that reward closer examination rather than immediate recognition, gemstones with latent optical complexity begin to hold greater relevance. because sometimes the most compelling materials are those that continue to reveal structure long after first impressions have stabilized. Number 6 reveals a gemstone whose darkness originates not from radiation exposure or optical density, but from a highly specific trace element balance that rarely stabilizes under natural conditions. Ranked 6th, black sapphire, when trace elements silence color instead of creating it. Color in corundum typically announces itself with clarity. Chromium produces red and ruby. Iron and titanium combine to create blue sapphire. Vanadium may introduce violet undertones. But in rare conditions, iron concentration becomes dominant enough to suppress nearly the entire visible spectrum, leaving behind a surface that appears almost completely black. Black sapphire emerges from this imbalance. Rather than displaying vivid hue, the crystal absorbs light so efficiently that color becomes secondary to structure. The result is not simply a dark gemstone, but a corundum specimen whose chemistry has shifted away from visual intensity toward compositional restraint. Iron content plays a defining role in this transformation. As iron concentration increases within the crystal lattice, electronic transitions absorb broader wavelengths of visible light. When absorption becomes sufficiently strong across multiple wavelength ranges, the gemstone begins to lose distinguishable color identity. Yet, unlike opaque materials that block light entirely, many black sapphires retain subtle internal translucency under strong illumination. This distinction matters. Under magnification or directional light, faint zoning patterns may appear, revealing growth structures formed during crystallization. These internal features provide evidence that the gemstone's darkness developed gradually rather than through external coating or treatment. Such details contribute to collector interest. Because corundum is among the most studied gemstone groups in mineralogy, deviations from expected color behavior often attract attention from gemologists seeking to understand formation conditions. High iron environments capable of producing stable corundum crystals are less common than those generating more recognizable sapphire colors. Pressure, temperature, and elemental availability must converge within a narrow window. Too little iron, and the crystal expresses blue or green tones. Too much, and crystal growth may be interrupted before gem-quality material forms. Black sapphire occupies a boundary between these outcomes. Its presence suggests conditions balanced precisely enough to maintain crystal integrity while altering optical response. In jewelry design influenced by architectural minimalism and neutral palettes, materials with this level of visual restraint integrate seamlessly into compositions emphasizing proportion rather than decoration. Instead of dominating attention, the stone supports overall structure. Quiet luxury often favors materials that reveal their complexity gradually. Black sapphire aligns with that preference. It carries the durability associated with corundum, one of the hardest mineral groups used in jewelry, while presenting a surface aesthetic that avoids visual excess. The stone communicates permanence without requiring explanation. As the hierarchy of dark gemstones continues to expand beyond familiar categories, distinctions between opacity, absorption, and structural composition become increasingly relevant. Because darkness alone does not define rarity, the mechanism creating that darkness often determines how the material is valued. Number 5 introduces a gemstone frequently dismissed as common, yet possessing a crystalline architecture whose complexity rivals far more widely recognized minerals. Ranked 5th, black tourmaline, complexity hidden inside a stone. Most people overlook. Familiarity often creates the illusion of abundance. Few dark minerals appear as frequently in raw crystal form as tourmaline, particularly the iron-rich variety known as schorl. Long prismatic crystals with deep vertical striations are widely recognized, often displayed in mineral collections or incorporated into contemporary jewelry that emphasizes natural geometry. Because of this visibility, the material is often categorized too quickly. Black tourmaline schorl belongs to one of the most structurally complex mineral groups used in gemology. Its chemical formula reflects a multi-element composition involving boron, silicon, aluminum, iron, sodium, oxygen, and hydroxyl components arranged within an intricate crystal lattice. Tourmaline does not form through simple geological conditions. Its crystallization typically requires boron-rich environments often associated with granitic pegmatites, geological formations already known for producing minerals that develop under chemically specialized circumstances. Within these environments, elemental availability must remain sufficiently stable for elongated crystal growth to proceed uninterrupted. The vertical striations visible along the crystal faces record incremental growth stages, preserving structural information about the conditions present during formation. Each line reflects a change in environment, temperature, or chemistry. Few materials capture geological variability so clearly in their external morphology. In darker scroll specimens, iron concentration increases light absorption, producing the near-black coloration associated with the variety. Yet beneath this visual simplicity lies a structure whose symmetry and compositional balance rival many transparent gemstones considered more traditionally valuable. Collectors attentive to crystallography often recognize this distinction. Rather than evaluating value purely through brilliance or color saturation, attention shifts toward formation and complexity in structural integrity. Well-formed scoral crystals display sharp terminations and consistent prism development, suggesting uninterrupted growth environments that are statistically uncommon. Even minor distortions in chemical equilibrium can interrupt crystal formation prematurely, resulting in incomplete or fractured specimens. Achieving both structural clarity and substantial crystal size requires environmental stability across extended geological timeframes. This combination of conditions is less predictable than surface appearance might suggest. As minimalist design aesthetics increasingly favor raw geometry and material authenticity, tourmaline's natural crystal architecture aligns with broader cultural movement toward objects that emphasize formation process over decorative refinement. Instead of concealing its origin through faceting, the material presents its structure openly. Such transparency often resonates with collectors seeking materials that communicate complexity without relying on optical spectacle. Understanding tourmaline's position within the quiet luxury spectrum requires recognizing that value does not always correspond with visual rarity. Sometimes the most sophisticated materials are those that appear common only because their structural significance remains underappreciated. When familiarity gives way to closer observation, assumptions about abundance often begin to shift. Number 4 introduces a gemstone whose rarity is not measured in chemistry alone, but in geological time spanning billions of years. Ranked 4th, Nuummite, a gemstone formed before complex life existed. Age rarely presents itself visibly. Most minerals reveal little about the immense geological timelines required for their formation. Surface appearance alone seldom communicates whether a crystal developed millions of years ago or billions. Nuummite exists within a very different temporal category. Composed primarily of anthophyllite and gedrite, this metamorphic mineral formed approximately 3 billion years ago under conditions present during the early evolution of the Earth's crust. At that stage in planetary history, atmospheric composition, geothermal activity, and tectonic dynamics differed significantly from those observed today. Complex life had not yet emerged. Continents had not stabilized into their present configurations. The environments capable of producing Nuummite were both rare and transient, requiring high-grade metamorphic processes in which pressure and temperature altered pre-existing minerals into new structural arrangements. These transformations occurred deep within ancient geological formations, now exposed primarily in Greenland, one of the few known localities where gem-quality material has been documented. Geographic limitation contributes to rarity. Temporal distance intensifies it. Unlike gemstones valued primarily for optical performance, Nuummite derives much of its significance from its association with early planetary development. Within polished surfaces, subtle iridescent flashes may appear under directional lighting, typically presenting gold or bronze-tone reflections embedded within an otherwise dark matrix. This optical behavior results from lamellar structures formed during metamorphic recrystallization, producing thin internal layers capable of interacting with light at specific angles. The effect remains understated. Movement reveals it gradually. Observation becomes part of the experience. Collectors drawn toward materials carrying geological narrative often regard Nuummite as a mineral connecting contemporary objects to deep time, an interval so vast that conventional measures of rarity begin to feel inadequate. While many gemstones communicate scarcity through limited production or restricted mining locations, Nuummite introduces an additional dimension. The conditions required for its formation are unlikely to repeat in precisely the same way within the modern geological cycle. Its existence reflects environmental parameters no longer commonly present. In design contexts aligned with quiet luxury, materials linked to long-term natural processes often carry particular resonance. Their significance does not depend on visual intensity. Instead, value emerges through association with continuity and endurance. The stone does not need to appear rare. Its history ensures that it already is. As collectors increasingly prioritize materials offering narrative depth beyond immediate appearance, gemstones connected to early planetary history acquire renewed relevance. Because luxury, in its most restrained form, often aligns with permanence rather than novelty. Number 3 introduces a gemstone whose dark body tone does not conceal light but amplifies it, revealing how controlled darkness can enhance optical complexity rather than diminish it. Ranked third, black opal, darkness that exists to reveal light, not hide it. Contrast determines visibility more than brightness alone. In environments where light interacts with layered internal structures, darker backgrounds can increase the perception of color rather than suppress it. This principle appears repeatedly across visual sciences, from photography to material engineering, and finds one of its most refined natural expressions in black opal. Unlike fully opaque gemstones, black opal does not derive its value from surface darkness alone. Its body tone, typically categorized between dark gray and deep black, acts as a neutral field against which spectral color phenomena become more pronounced. Microscopic silica spheres arranged within the opal's internal structure diffract incoming light, separating wavelengths into shifting color patterns that change with viewing angle. This interaction produces the phenomenon commonly described as play of color, a defining characteristic of precious opal varieties. When this optical effect occurs within lighter body tones, color contrast remains softer. When it occurs within darker material, visual separation intensifies. Color appears more vivid, not because more light is present, but because background absorption reduces competing visual information. The result is controlled luminosity emerging from an otherwise restrained exterior. Among geological sources, Lightning Ridge in New South Wales, Australia, has historically produced many of the most sought-after dark body tone opals. Geological conditions within this region allowed silica-rich solutions to deposit repeatedly within cavities of sedimentary rock, gradually forming ordered sphere arrays capable of diffracting light consistently. Each step in this process required environmental stability across extended periods. Minor variations in silica concentration, temperature, or water availability could interrupt sphere formation, preventing the development of coherent diffraction patterns. This sensitivity contributes to the rarity of high-quality material. Within quiet luxury aesthetics, black opal occupies a distinctive position. Its external appearance remains composed, often revealing little at first glance. Movement introduces transformation. Subtle shifts in viewing angle allow color structures to emerge gradually, rewarding observation rather than demanding attention. This behavior aligns with broader preferences for materials whose complexity unfolds over time, rather than presenting immediate visual intensity. Collectors often value stones that maintain visual interest without relying on constant brilliance. Black opal demonstrates how darkness can function as an enabling condition rather than a limiting one. Instead of competing with light, the material organizes it. Instead of amplifying brightness indiscriminately, the structure directs perception toward controlled chromatic variation. Such qualities resonate within design philosophies emphasizing balance, proportion, and restraint. As gemstone preferences continue evolving beyond conventional expectations of sparkle, materials capable of revealing depth without visual excess gain relevance. Because sometimes the most compelling display of color begins with the decision to limit it. Number 2 introduces a material whose internal structure challenges traditional definitions of diamond itself, suggesting that rarity may also emerge from unresolved scientific questions. Ranked second, Carbonado, the diamond that does not behave like one. Classification becomes complicated when a material shares a name, but not the expected structure. Most diamonds form as single crystals composed of carbon atoms arranged in a highly ordered lattice, created under extreme pressure deep within the Earth's mantle. This structural uniformity produces the optical clarity and brilliance typically associated with traditional diamond gemstones. Carbonado challenges that expectation entirely. Rather than forming as a single crystal, Carbonado develops as a polycrystalline aggregate, a network of numerous microscopic diamond grains fused together. This configuration produces a dense, porous internal structure lacking the transparency seen in conventional diamond material. Light entering Carbonado encounters multiple crystal boundaries, scattering in unpredictable directions rather than passing through a continuous lattice. The result is a surface appearance that absorbs illumination instead of amplifying it. Optical silence replaces brilliance. Geographically, Carbonado has been discovered primarily in Brazil and the Central African Republic, often within sedimentary deposits rather than typical kimberlite pipes associated with diamond formation. Its origin remains a subject of ongoing scientific discussion. Some hypotheses propose formation through high-energy impact events, while others suggest unique mantle conditions capable of producing polycrystalline carbon masses distinct from traditional diamond growth patterns. Isotopic analysis has revealed characteristics differing from many conventional diamonds, contributing to continued debate regarding its precise geological history. Such ambiguity adds another dimension of rarity. Collectors often assign significance not only to confirmed scarcity, but also to materials occupying unresolved categories within scientific classification. Carbonado exists at this intersection. It is simultaneously diamond and not diamond, sharing chemical identity while diverging structurally. Its hardness remains substantial, yet its internal architecture resists the faceting styles used to maximize brilliance in transparent stones. Instead, Carbonado tends to be polished into smooth surfaces that emphasize texture rather than light performance. Within the framework of quiet luxury, materials associated with unresolved scientific narratives often carry particular appeal. They suggest depth beyond visible characteristics. They imply ongoing discovery rather than completed understanding. Unlike gemstones promoted primarily through marketing familiarity, Carbonado circulates within more specialized segments of the gem trade, where material identity and geological context often carry greater weight than visual recognition. Its rarity does not depend on fashion cycles. Its significance does not rely on widespread visibility. Instead, Carbonado represents a category of material whose value emerges from deviation itself. Deviation from structural norms, deviation from conventional formation models, deviation from expectations associated with one of the most recognizable gemstone names in the world. As collectors increasingly explore materials positioned outside traditional hierarchies of brilliance, the definition of luxury continues to expand, because sometimes rarity is defined not only by scarcity, but by uncertainty. Number 1 reveals a gemstone whose presence has already become synonymous with understated prestige, a material widely recognized within high-end jewelry, yet rarely associated with visual excess. In first place, Tahitian pearl, recognition without display. Status does not always rely on visibility. Certain materials communicate value through association rather than spectacle, becoming recognizable primarily within circles already familiar with their significance. Among dark gemstones, few objects illustrate this principle more clearly than Tahitian pearl. Produced by the black-lipped oyster Pinctada margaritifera, Tahitian pearls develop within marine environments where biological processes gradually deposit microscopic layers of nacre around an internal nucleus. Over time, these concentric layers create a surface capable of reflecting light with a soft, diffuse luster distinct from the sharper brilliance observed in faceted stones. The color range commonly described as black often includes complex overtones, subtle variations of green, aubergine, silver, or peacock hues that shift gently under changing light conditions. This restrained optical behavior contributes to their long-standing presence within high-end jewelry design, emphasizing balance rather than intensity. Unlike gemstones requiring cutting and polishing to achieve their final appearance, pearls emerge already formed through organic growth processes that cannot be accelerated without altering internal structure. Each specimen reflects environmental variables such as water temperature, nutrient availability, and biological health of the host mollusk. Even under controlled cultivation conditions, the outcome remains partially unpredictable. Shape, overtone distribution, surface smoothness, and luster quality depend on biological responses that resist full standardization. This variability introduces a rarity mechanism distinct from geological scarcity alone. No two pearls develop identical internal layering patterns. Each nacre structure influences the way light interacts with the surface, producing a visual softness often associated with composure rather than brilliance. Within quiet luxury aesthetics, such restraint carries particular relevance. Materials that avoid excessive reflectivity allow design emphasis to remain on proportion, texture, and continuity across an entire piece, rather than focusing attention on a single focal point. Tahitian pearls integrate into compositions without disrupting visual balance. Their presence becomes apparent gradually. Collectors frequently associate them with confidence that does not require explanation. Unlike gemstones whose value depends on immediate recognition through intense sparkle or widely promoted rarity narratives, Tahitian pearls occupy a position supported by long-standing acceptance within high jewelry traditions. They appear regularly in collections emphasizing refined understatement. They signal familiarity with material nuance rather than preference for overt display. In many ways, Tahitian pearls represent the culmination of a broader shift occurring across luxury categories, a movement away from materials designed primarily to attract attention toward those capable of sustaining long-term aesthetic relevance. Recognition occurs quietly. Appreciation develops through proximity. Value becomes self-evident to those already accustomed to observing subtle distinctions. As gemstone preferences continue evolving, the most influential materials may not be those that appear extraordinary immediately, but those that maintain their presence consistently across changing stylistic cycles. Because quiet luxury rarely introduces itself loudly, it simply remains visible to those already looking closely enough. Black diamonds became popular because they were easy to recognize. But recognition has never been the only way rarity reveals itself. The gemstones in this list demonstrate a quieter form of distinction, one shaped by geological precision, structural complexity, and conditions nature rarely repeats exactly the same way twice. Some express rarity through atomic substitutions invisible to the eye, some through formation environments separated by billions of years, others through optical behavior that only becomes apparent under careful observation. Quiet luxury rarely depends on immediate visibility. It emerges through materials that remain relevant even when trends change. Stones that communicate presence without requiring explanation. Objects whose value becomes clearer over time rather than at first glance. Because not all rarity announces itself loudly, and not all luxury is meant to be immediately understood.